Let's look at some applications of exponential and logarithmic functions. Before we do an example, let's do a little recap. Suppose b is constant. We want to take the derivative with respect to x of a function that looks like b to the u. The formula is we're going to take ln of b, meaning ln of our base, times b to the u times the derivative of u with respect to x. If our base happens to be e, then we get an even simpler formula. The derivative with respect to x of e to the u is equal to e to the u times du by dx. This formula is simpler because ln of e is equal to 1. Let's say we wanted to take the derivative with respect to time of e to the 9t. Then our derivative is going to look like e to the 9t times the derivative of the exponent with respect to t, which is going to be 9. And typically we'll write the coefficient at the beginning rather than writing it at the end of the expression. First example, a metal bar is heated and then allowed to cool for t minutes. Its temperature T in degrees Celsius is given by the following formula. Find the time rate of change of temperature after 6.0 minutes. Notice that we're using little t for time, capital T for temperature. Well, we're asked for the rate of change of temperature with respect to time, so symbolically we're going to write that as d capital T by d little t. And taking the derivative of capital T, we're going to get 84 times the derivative of the exponential function, which is going to look like e to the minus 0.31t times minus 0.31. Now to finish off, we have to evaluate our derivative at little t equal to 6.0. So let's plug in. We've got 84 times negative 0.31 times e to the following exponent, negative 0.31 times 6. So plugging this entire expression into our calculator, we're going to get a value of negative 4.1. And if we think about the units, we've got the units of temperature, which are degrees Celsius, divided by the units of time, which are minutes. So final answer, negative 4.1 degrees Celsius per minute is the time rate of change of temperature after 6.0 minutes. Let's do a quick recap of logarithmic functions. The derivative with respect to x of log base 3 of x to the fourth plus 7 is going to have 3 parts to it. We'll go 1 over ln of the base times 1 over our inside function times the derivative of our inside function, which would be 4x cubed. So we could write our answer more concisely as 4x cubed over ln 3 times x to the fourth plus 7. Now, suppose we were taking the derivative with respect to x of ln x to the fourth plus 7. Here we have to remember that ln just means log base e. So we're going to get a simpler expression here. We'll have 1 over our inside function, which is x to the fourth plus 7, and that's going to get multiplied by the derivative of the inside function. So we could write that more concisely as 4x cubed over x to the fourth plus 7. Remember here that ln of e is equal to 1, and that's why we're not getting that constant coefficient. Example 2, the energy E in joules dissipated by a resistor after t seconds is given by the following function E. When is the energy maximized? Meaning at what time value t is the energy maximized? Let's start by finding E prime of t. Because we're dealing with a line function, the derivative is going to look like 1 over the inside function 1 over t plus 2 times the derivative of the inside function, which is 1. Then we've got minus 0.125. Now we're going to set e prime of t equal to 0. By setting that equal to 0, we're going to be finding critical points. So 1 over t plus 2 minus 0.125 is equal to 0. And at this point, we'd like to solve for t. The easiest way to do this would be to move the decimal over to the right side. So we've got 1 over t plus 2 is equal to positive 0.125. And because t is in the denominator, the easiest way to solve for t now is to take reciprocals of both sides. So t plus 2 is equal to 1 over 0.125. And then we've got t is equal to 1 over 0.125 minus 2. So t is equal to 6. And that would be measured in seconds. So t equals 6 seconds. Now if we wanted, we could check that this does indeed correspond to a maximum. If we wanted to check that this time value corresponds to a maximum, then we could use the second derivative test. We'll go back to e prime of t, and if we take the derivative of this, we'll have e double prime of t is equal to minus t plus 2 to the power negative 2 times the derivative of the inside function, which is 1. And then we need to plug in our time value 6 and check the sign. So we're really just interested in whether this is a positive or negative quantity. It comes out negative. And what that tells us is that our function e is concave down at that point. And just by drawing the picture, we can see that if the function is concave down, then this will correspond to a maximum. So that's how the second derivative test works. If your second derivative is negative, then you know that you've got a max. So we can say for sure, yep, this does correspond to a maximum.